I'm now going to continue my video series on Common Core Algebra 2. And what would surprise a lot of people is they'll sit there and they'll say, well, you only got 2 views on a particular video, or you only got 3 views on a particular video. What they do not realize is that a lot of people will watch my videos not necessarily on my main YouTube channel, but they'll watch my videos on some place like Facebook or whatever. They'll watch it on another site, which then shows it to them before it gets to me. The thing is that YouTube doesn't count views, okay? It doesn't really count views if somebody sees it from another place. And you also have to keep in mind, some people download my videos and then they show it to other people. Well, I don't get a view count for that. So more people are actually watching my videos than what I have on my official counts. So see, that throws things off a little bit. Now the other thing people say is, well, I look down through all your comments and I hardly see anything. Well, not everybody gives me word. They don't send word back to me necessarily through a comment. Some do, others don't. Some people send me comments through private emails. So to stand there and say, well, you're not getting hardly any comments or hardly any views, well, that's just not the case. The reality is I'm not always getting all the counts, and I'm also not always getting comments under the videos. Sometimes I get personal letters. Some people just don't want to be public. That's fine. I understand that. I fully comprehend that. So just because you see a low view count on my video doesn't mean that not anybody's watching. It just means that maybe they're watching on Facebook instead of on my main YouTube channel. I don't get a view for that. Or maybe somebody's downloaded the video and showed it to their friends. I don't get a view for that. See me? But sometimes I still get a response anyway. So, don't misrepresent my view count or my comments under my videos as a failure on my videos, because it's not necessarily the case. And right now all I'm doing is making dang sure that you can get a full view of my little board here. You are. Okay, good. Alright. Now then, we're going to start this lesson with a word called binomial. Now what is this word? Well, it starts with a Latin prefix, and then it has a root word, and this is the root word right here. Now this is actually a Latin suffix. We'll get into that later. But what is the Latin prefix of bi? Well, the Latin prefix of bi actually means 2. Okay? Now, the root word. The root word is right here. It's nomos. The root word is actually spelled nomos. Now here's the problem. The root word nomos, okay, is Greek, not Latin. And it actually means part. It's a piece. So, what we have here, let's say we have x plus y. We have 2 terms here. This is a binomial. Why is it a binomial? Because it has 2 pieces. This is one piece, this is one piece. That makes it a binomial. Now what if we had like that? That's a trinomial. Tri in the Latin means 3. And if I recall correctly, bi and tri also can be found in the Greek. Bi meaning 2, tri meaning 3. So, actually, you can trace all this back to the Greeks. Because a lot of this mathematics came from the Greeks. Came from Greece. Look it up. Might learn something about the country. Might learn a few things. Okay. So, let's get into this. We're talking about quadratic functions in the vertex form. Now, the first thing that I was told by one of my students in a private email, not in a comment, but in a private email, because like I said, some of these people don't want to be recognized, is that I got a sign wrong in an equation that I was showing to you the last time. And they were correct. I did get a sign wrong, and so we're going to do this all over again. But before we do, that same person also said that they didn't quite comprehend how the quadratic formula actually works. Okay. So, we're going to take them through it. Now then, let me ask you something. And this is to the person that wrote me the email. What is 2 plus 2? Well, of course, it's 4. What's 4 plus 4? Why, that's 8. And what's 4 times 4? Well, that's 16. So 2 plus 2 is 4, 4 plus 4 is 8, and 4 times 4 is 16. This is basic arithmetic right here. Most people know this. Most people. I really hate to tell you this, people, but I do actually have people that do not know basic arithmetic. And I can prove this because one of my most highly rated videos is how to count change. I kid you not, I still get a lot of hits on that one. So they don't know this. So doing Algebra 2 for them is, well, it's next to impossible. Why? Because they don't even know basic arithmetic. Now, if they don't know basic arithmetic, they're never going to make Algebra 2. I can guarantee you that. And no, they're not going to make through basic arithmetic with jumps of 10. That's a piece of garbage. It needs to be thrown in the trash. It needs to never be remembered again. So get rid of the jumps of 10. If you want to get into real mathematics, do it this way. Okay? So, let's erase this. Now let me ask you something. If you have 2 plus, whoops, let's do this right here. When I get excited, sometimes I don't draw things right. 2 plus 2 times 2 plus 2 equals 16. You say, well, where does all that come from? Well, we can say that 4 times 4 equals 16. Now, would you agree with me that 2 plus 2 is 4? Yes. Would you agree with me that 2 plus 2 is 4? Yes. So all we did was we broke up this 4 into 2 plus 2, and we broke up this 4 into 2 plus 2. So this equation here is exactly the same as this equation, except we broke up the 4's into 2 plus 2. That's all we did. Okay. Now, let me show you how this one is going to work this way. We're going to take the first two terms, 2 and 2 here. What is 2 times 2? Well, that's 4. What is 2 times 2? Well, that's 4. That's right. This 2 times this 2 is going to make 4. What is this 2 times this 2? Well, of course, it's going to be 4. Oops. Hold on. And what is this 2 times this 2? Well, of course, it's going to be 4. What is 4 plus 4 plus 4 plus 4? Well, that's going to be 16. That's how that works. Are you getting it yet? Do you comprehend all this? Good. Okay. So now we're just going to make things a little more complicated. So wait a minute. What do you mean you're going to make it complicated? A variable is nothing more than a number in disguise. So now we're going to have this. Whoops, 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 whoops. That's not right. So, if we remove the costume from letter A, it's going to reveal itself as a 2. If we remove the costume from letter B, it's going to be 2. If we remove the costume from letter C, it's going to be 2. If we remove the costume from letter D, it's going to be 2. So again, the whole thing continues to work out. So now what we have here is AC, okay, plus AD plus BC plus BD. And I've already stated that every one of these letters represents the number 2. 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4. Add them all together, and boom. Remember, you are supposed to multiply and divide numbers before you add and subtract them. That's an arithmetic rule, and Euclid proved this. If you go back to my Euclid Elements videos, you'll see this. So, what is AC? Well, it ends up being 4 because 2 times 2 is 4. What is AD? It ends up being 4 because 2 times 2 is 4. What is BC? 2 times 2 is 4. What is BD? 2 times 2 is 4. Makes 16. So, right now, we have 4 terms. AC is the first term, AD is the second term, BC is the third term, BD is the fourth term. There's your 4 terms. Okay. Now, what if we get a little more fancy? We're going to get a little more fancy? You bet. We know that both A and C equals 2. Well, we can also say that A equals C, because after all, if A is 2 and C is 2, then they're both equal. We can also then say that A equals C equals X. So now, wherever you find the letter A or you find the letter C, we're going to replace it with the letter X. Well, I find a little letter A here, so we're going to replace it with the letter X. And you see this little letter C over here? We're going to replace it with the letter X. Okay. Now then, what if we rewrite all this? Well, what's X times X? Well, it becomes X squared. Why is that an X squared? Well, I explained this in Euclid's Elements. I really did. It's because of a physical square. Now let's imagine that this physical square was 2 inches long by 2 inches wide. There's your length times the width. So you multiply this times this, and you get that. So this here represents that square. That's what it does. Okay? So this is actually a variable with an exponent. That's what it is. Are we getting it now? Let me erase this. That's where they came up with the principle of squaring a number. They drew a physical square, they took its length and its width, they multiplied it together, and that's where they got the symbol. That's exactly where they got it. So now we have X squared plus dx. Why dx? Because we're going to multiply the x times the d. Now, what about bx? B times the x. B here, x here, multiply together, we get it. Plus b, whoops. Okay. Are we getting it so far? Of course. So, what we have here is x squared plus dx plus bx plus bd equaling 16. And since we know all of these variables represent the number 2, then what do we have? Well, 2 squared is 4, because when you multiply 2 times 2, you get 4. What do you got here? 2 times 2 equals 4. 2 times 2 equals 4. 2 times 2 equals 4. Add them all together, they become 16. That's exactly how you get it. But we're going to get a little more fancy. We're now going to say, watch this. What we're going to do is we're going to say that b equals d, which also equals y. So guess what we're going to do? We're going to replace b and d with y. Anyway, here we go. Y, y, there you go. So now what do we got? We got x squared. Again, why x squared? Because of the square, which will literally be x times x. That's what it is. Now we have xy. Why do we have xy? Because we took this x times that y. Why do we have this xy? Because we multiplied this x times that y. Now why do we have y squared? Because we multiplied this y times this y and we made a square. And the length of the sides of this square are going to be y. The length is y, the width is y, same thing. And that's where we got it from. Again, this is not rocket science, people. Not at all. 2 times 2 is 4. Why? Because 2 raised to the power of 2 is 4. Gee, if each one of these sides is 2, well, there you go. This is what they call a square area. This is a square area. That's where they got it from. It's from farming. They had to come up with square areas. As a matter of fact, that's why we do all these quadratics in the first place, because what they're wanting you to do, and this was what I got out of Euclid Book 2. Remember I had that reference to Euclid Book 2 in my last video? This is what I'm talking about. What they did was they reshaped a rectangle into a square, but the area inside that rectangle was exactly the same as the area inside that square. That's why they did all this. What they did was they said, well, okay, we need this piece of land, so we're going to give you this piece of land, which is the equivalent of the piece of land we're taking from you. So they just reshaped the farmer's land. He still had his land. He had the same amount and the same kind of land as the other part. And they took the other part. And they probably would be the government. The government, probably the Roman government, would come in and say, look, we need this part of your land, so we're going to give you this part of our land to compensate you for the part of land we're going to take away from you. So it ended up being the same acreage. So nobody got ripped off. Well, that's the concept anyway. Of course, that didn't always work out, but that's the general concept. Okay. So, are you seeing how this is actually starting to work? Now, we have to talk about coefficients. When you're talking about the quadratic formula or any quadratic equation, okay, especially the quadratic formula, there are coefficients. And let me just change this a little bit. Let's go ahead and change this. Okay. We have x squared plus 2xy plus y squared. Alright. Now what is the coefficient of a? In a quadratic formula equation, this is going to be 1. If it's not 1, you have to factor it out until it becomes 1. Okay? What's the coefficient of this term right here? Well, that's 2. What's the coefficient of this term right here? It's 1. So we have the coefficient of this is 1, the coefficient of this is 2, the coefficient of this is 1. Now this becomes very important. Because let's say you're trying to come up with a perfect trinomial square. How do we come up with a perfect square trinomial? Well, let me try to help you out with that one. Alright, what they tell you to do, let's say we have x squared plus 2x plus 16 equals 0. Now we have to come up with a perfect square trinomial. Well, the first thing we're going to do is we're going to have x squared plus 2x equal, well, we're going to put the equal sign way over here. Okay. Now then, what they want you to do is they want you to take this coefficient and they want you to divide it by 2 or multiply it by 1/2, either way. Okay? Now then, you say, well, why do they want you to do that? What is 2x? Well, 2x in this particular case is x plus x. So half of 2x is x. Okay? So when you're going through here and you're multiplying like this, okay, then this is one term, this is the other term. So the first thing you have to do is reduce this down to one term. And that would be this one. We're just going to pick one of these. And we're going to pick this one right here. So you're reducing it down to its one term. Now that's pretty good. So now 2 divided by 1/2 is 1. Okay? If you take 1/2 times 2 over 1, you get 1. But the 1 is not enough. Because when you multiply this term by itself, you're going to get a square. You're going to get a square when you multiply this times itself. Now, I already showed you that earlier in this video. So now that we got this 1, well, we're going to square the 1, and we're going to come up with 1. But you must treat this equal sign like a set of scales. And on my Speed Learner fan page, when I discussed this, I left a hyperlink to a photo. Well, actually, yeah, it is actually a photo. It's a photo of a set of ancient scales. What scales would it look like? Well, kind of like what they look like on the Statue. Well, not even the Statue of Liberty, because the Statue of Liberty doesn't really hold scales. But have you ever seen Lady Liberty? You ever seen a statue of Lady Liberty and she's holding up those scales? That's it. Okay? So, if we've added 1 to this side of the equation, guess what we have to do here? We have to add 1 to this side. So, 16 plus 1 is 17. And then we have x squared plus 2x plus 1 equaling 17. Now, what is this? Well, I'm going to show you. Let's erase this top part here. So, what is x squared plus 2x plus 1? X plus 1 Boy, that's ugly. X plus 1, X plus 1. How do we know it's x plus 1 times x plus 1? X times x is x squared. 1x plus 1x is 2x. 1 times 1 is 1. That's how we know. So we could actually rewrite this as x plus 1 times x plus 1 equals 17, and we'd have the exact right equation, just like that. See what I mean? But this right here, what I just showed you here is how to complete the square. That's what they're talking about. When you complete the square, you're going to take the coefficient here, multiply it by 1/2, then square the result, and then you got it. That's what they're talking about. Now, I know in some of these dang videos, and you've seen this maybe in your homework assignment, they'll give you, let's say they give you x squared plus 2x and then they say to you, alright, we're going to complete the square in a different way. They're still going to take the coefficient, which is 2 over 1. They're going to multiply it by 1/2, which of course gives you your 1. They're going to multiply it again by 1. Okay, and what they say is that if you add this, we have to subtract it. Why? Because if you increase the value of this side of the equation by 1, you then also have to subtract 1 because the 1 minus 1 cancels each other out. Now, if you're going to go through all that trouble, why don't you just add this 1 over here? Instead of trying to add 0 to this side of the equation, why don't you just add 1 to the other side? That's stupid. Now, the only time that becomes valuable is when you don't have an equation like this, you start having this. Okay? Then it becomes a little more valuable because it's really difficult to get rid of that term. Then you could then add 1, subtract 1. You could do that. Then you just factor this out, and you'd have, of course, have x plus 1 squared minus 1. Okay? That's when it becomes valuable. So, either you can add a certain amount to both sides of an equation, or you can add and subtract the same amount from one side of the equation and you still get the same result. But that's what they're talking about there. Whew. Same fundamental concept, just a lot of stupidity. They just want to make it more complicated for you. Oh well. Anyway, back to this. What did Descartes say? Well, what he did was he had z squared equaling az plus b squared. That's what he had originally. This is where I started messing up. You have z squared minus az minus b squared. And that began all my troubles in the last video. Okay. Now we did factor out the coefficient of this right here, which is 1. Okay. The coefficient of the first term is 1. Alright. So this is the first term, the coefficient is 1. So now we have 1 multiplied by z squared minus a over 1z minus b squared. Of course, all of this, whoops, not this. This equals 0. This, of course, equals 0. Okay? Now then, we went ahead and we moved that back over there. It was kind of silly of us not to do that. But anyway, now we got okay. So now we have to complete the square over here. So how are we going to complete the square? Well, we're going to erase all this. I can only write so much. So now what we're going to do is we're going to take 1/2 times a over 1. And that's going to make a over 2. And of course, what we want to do is we want to square the a over 2 right over here. So what's a times a? It's a squared. What's 2 times 2? That's 4. So now we got to put this a squared over 4 into our original equation. So now what we got is z squared minus a over 1 a over 1z plus a squared over 4 equaling a squared over 4. Remember, we added the same amount both sides of the equation plus b squared over 1. Alright. Now, we're going to multiply a squared over 4 times 1 over 1 because of this term right here. Okay? So that z squared minus a over 1z plus a squared over 4 equaling a squared over 4, because a squared over 4 multiplied by 1 over 1, well, a squared times 1 is what? A squared. What's 4 times 1? That's 4. But now we have to multiply b squared over 1 by 4 over 4. Why are we multiplying b squared over 1 by 4 over 4? Because of this term right here. That's right. So, what are we going to come up with when we do that? We're going to come up with, well, what's b squared times 4? It's 4b squared. What is 1 times 4? That's going to be 4. And why are we doing all this? Because now our denominators are exactly the same. If our denominators are exactly the same, now we can add everything up. Wow. Aren't we just fancy? Now, z squared minus a over 1z plus a squared over 4 now equals a squared plus 4b squared over 4. That's what it equals. So far, so good. Alright. Now the next step is that we're going to factor this out. We're going to factor this into the FOIL method. We're going to use the FOIL method to factor this out. That's what we're going to do next. Okay. Let's factor it out. So now we have z minus a over 2. I think. May not be right after all. Because what you would actually have is negative a over 2 plus negative a over 2, and okay, which would be that would actually be right, because the 2's would cancel each other out, making that. So yes, I was right. I was 100% correct. I thought I was wrong. I was right. What's negative a over 2 plus negative a over 2? Well, a plus a is 2a, and so the 2's cancel each other out, making a over 1. So yes, I was right. Boy, I feel good now. Okay. Alright, and by the way, this is not right. So, z minus a over 2 squared equals this. So now, sometimes you have to double check yourself, make sure you're doing it right. So now, we're going to square root both sides. How do we square root both sides? Well, now we have z minus a over 2 equaling the square root of, we can't really square root the top part of this, a squared plus 4b squared, and that's because of all these terms, dividing that by, well, what's the square root of 4? Well, that's going to be 2. That's what it's going to be. Alright. Now then, does this term look exactly like that term? Well, of course it does. So now what you have is z, and we're going to move this term, this one right here, we're going to move that term to the other side. So z now equals a plus the square root of a squared plus 4b squared over 2. And that's how that works. So as you can plainly see, my equation still worked, even though I had to make a slight, I had to change the b from a positive to a negative. But it still worked out. And this looks remarkably similar to the quadratic equation, to the quadratic formula that you have in your textbooks. And that's what that was all about. Okay. Now let's go on with this lesson. Now that you have a full comprehension of what you're dealing with, now remember that when you have a quadratic function, if it possesses a positive vertical stretch, okay? Now the quadratic function in the vertex form goes something like this. You have f of x, you have a, equals a times x minus h squared plus k. Now, if this a, remember this a is a variable, okay? And if that variable, if you take the costume off this variable and the number underneath is positive, then it's going to have a positive vertical stretch or compression. Okay? Whether it opens up like this or closes in like this, it's going to be in this shape. Now, if the number underneath this costume is negative, then it's not going to open up, it's going to open down. Like that. So whatever that A is going to determine whether this is going to open down or it's going to open up. Now, what is the vertex of this quadratic function? This is the x-coordinate, this is the y-coordinate of the vertex. That's why we put it in this form. Okay? Now, what is the axis of symmetry for a quadratic function? It's when x is exact same value as h. So when x is actually the same value as h, that becomes the axis of symmetry. So you can literally draw a line through the x-coordinate when it's equal to h. That's your axis of symmetry. Now, why will the x minus h squared always be positive? Because whether you, let's say that x minus h ends up being 5. Okay? Let's say that x was 6 and h was 1. Okay? Let's say x was 6 and h was 1. Well, 6 minus 1 equals 5. Well, you square 5 and you get 25. Like that. But let's say that x minus h ends up being negative 5. Who cares? Because as soon as you square that negative 5, it's going to become 25 anyway. So no matter which way you go, x minus h, once you square it, it's going to be positive. Always. And that's what that's all about. The reason why we write this in the vertex form is so we can actually draw a parabola. Now granted, you could still draw Descartes' circle and right angle triangle to show the quadratic formula and the quadratic function. You could do that. But if you want all the values for it, you're going to have to draw that parabola. Whether it be up or down. Doesn't matter either way. Well, are you mesmerized for today? I think you've learned quite a bit. Alright. That concludes my lesson for today. I will tell you more in a future video, so I want you to stay tuned.